NASA Langley Research Center, in collaboration with other NASA centers, is investigating technical concepts for allowing unmanned aircraft to have routine and safe access to the National Airspace System. Operators of unmanned aircraft systems, or UAS, such as NASA's Global Hawks and Predator B, deal with cumbersome regulations, which only allow them to fly in airspace that has been sterilized to keep other traffic from entering. What they really need is UAS integration, the capability to file and fly in the national airspace like any other aircraft. The most obvious difference between UAS and traditional aircraft is the lack of an onboard pilot. It is this difference that drives the problem of how to deal with the regulatory requirement that all pilots must see and avoid other aircraft. When applied to UAS, which substitutes surveillance sensors for human eyesight, this requirement is called detect and avoid. Referring to the same regulation, detect and avoid is defined as the capability of a UAS to remain well clear from and avoid collisions with other airborne traffic. Any detect and avoid concept must address the issue of what is meant in the FAA regulations by well clear. Although there is no precise regulatory definition, well clear implies at minimum enough separation to avoid collisions while also maintaining an additional margin for safety. UAS pilots do not have the same immersive visual cues as a see and avoid pilot. To address this challenge, NASA Langley has developed a detect and avoid concept for assuring self-separation of UAS from other aircraft. Collision avoidance and self-separation are different functions, but they can both be visualized as airspace volumes surrounding an aircraft in flight. For this discussion, the volumes are illustrated as centered on the UAS. The collision avoidance function is based on airspace that resembles a cylinder with a horizontal radius of 500 feet and vertical height of 200 feet. Within this so-called collision volume, avoidance of a collision can only be considered a matter of chance. Any aircraft entering the collision volume is considered a near mid-air collision. Aircraft outside of this volume are not necessarily considered well clear. At typical aircraft cruising speeds, an aircraft crossing just in front of another at the same altitude and missing by 501 feet just outside of the collision volume would be only seconds from colliding at its closest point of approach. Consequently, the self-separation function establishes airspace that is larger than the collision volume and is designed to provide a safer distance between the UAS and another aircraft, also referred to as an intruder. Any intruder outside of the self-separation volume would be considered well clear of the UAS, and the UAS pilot complying with detect and avoid would maneuver as necessary to keep intruders from entering this volume. As shown in this conceptual animation, the dimensions of the self-separation volume react to the relative motion of the intruder, thereby defining both when and how far the UAS must maneuver to remain well clear. Researchers at NASA Langley are developing tools that can assist UAS pilots with detect and avoid maneuvers. These tools use automation for what it does best, which is sensing, monitoring, and calculating, while leaving adaptive decision-making to UAS pilots and controllers who typically do these functions better and more easily than automation. In this concept, automated functions will detect and track the intruder's position and velocity, evaluate and prioritize the collision or self-separation risks, and indicate to the pilot whether some action is required. The UAS pilot will use the automated guidance to determine the appropriate action and coordinate with ATC before maneuvering as necessary to maintain separation. These actions are similar to those that would be taken by the pilot of a manned aircraft who sees and avoids. At the heart of this concept is a robust self-separation algorithm that has evolved over years of design iterations and testing. Currently known as Daedalus for For detect and avoid alerting logic for unmanned systems, the algorithm can identify situations where intruders have become threats and provide suggestive maneuver guidance to assist the UAS pilot in performing any necessary maneuvers. The guidance is depicted as maneuver bands on the UAS ground control station and shows headings, altitudes, and vertical speeds that will result in loss of well clear with identified intruders. In order to operate seamlessly in the NAS, Detect and Avoid must interoperate with the current Traffic Alert and Collision Avoidance System, or TCAS, which is mandated for most commercial aircraft in the U.S. TCAS utilizes aircraft transponder reports to make pilots aware of proximate traffic and also provides resolution advisories, or RAs, to warn pilots of potential collision threats. In order to avoid triggering unnecessary RAs from TCAS, Daedalus must detect encountered geometries that would cause a resolution advisory and take action early enough to avoid the RA. Air traffic controllers also play a crucial role in the development of Detect and Avoid. For aircraft under positive control, the well-cleared distance used by the UAS pilot must also satisfy controllers' criteria for safe separation between aircraft. These are just a few examples of the fine-tuning of the concept that must be done before it is ready for operational deployment. Experimental research conducted at NASA Langley to assess the performance of Detect and Avoid and its associated procedures helps to establish minimum operational performance standards required for UAS integration. The results of this research will have significant implications on the future of UAS operations in the National Airspace System.